Today we're going to be building on the work that we started in our last video where we built the molecular orbitals for water by now looking at systems that have more orbitals, specifically transition metals that have access to these d orbitals. It's important before you dive into today that you understand the three-dimensional shape of these d orbitals. That will be fundamental to our understanding of these molecular orbitals. But what we're going to be doing is we're going to look at our octahedral complexes. So specifically, this only applies to octahedral shapes for our complexes that we're looking at, and how these d orbitals can mix with the ligands themselves. So we're only going to treat our ligands like S-shaped orbitals today, and we're going to just look and see how our d orbitals can mix. So here is what our s orbitals look like when they are aligned along the axes in this octahedral arrangement. We can see that we have two ligands on each of our x, y, and z axes. Now we imagine that the transition metal is at the center at the origin. So we're going to break this up into a few different sections and look at the way that these orbitals interact with our ligand orbitals, right? We're looking at the d orbitals and how they interact with the ligands themselves. We're going to begin by looking at our dxy, dyz, and dxz orbitals. So again, these have the same shape, they're just oriented along different planes in our system. So here, our first orbital that we're looking at is our dyz orbital. And as we look at this rotation, we can see that actually all of our s orbitals, right, all of these generic kind of ligand orbitals, are aligned directly in the nodal planes of our d orbital. So we can see that there is a nodal plane that is along each of our principal axes here. So we have a nodal plane along our xy axis that contains 4 of our ligand orbitals, of these s orbitals. Similarly, we have a nodal plane that lies along our xz axis for this particular orbital, and this contains both of our ligand orbitals that are along our z-axis. So this means that there's no productive overlap of these orbitals with this particular d orbital, in this case dzy, or dyz, however we want to label it. Moving on, we'll see that the same exact situation occurs for both dxy and dxz. So let's look at xy first. As we see this rotation, as it's slowly processing, right, about on the screen, we can see that all of our ligands, again, directly fall inside the nodal planes of our d orbital. Because of this, we would assume there to be no productive orbital overlap, meaning there's not a spot where our s-shaped orbitals can directly interact with any of our d orbitals. So we would imagine that these would essentially be non-bonding interactions, right? There's no way that we can mix these orbitals, the dxy, the dxz, or the dyz orbitals, with any of our ligands. So let's look at what happens to our orbital diagram when we look at just these 3 orbitals. So with these 3 orbitals, with there being no productive overlap, right, there's no way for us to form a molecular orbital that involves both the ligand and these d orbitals. So these orbitals remain localized on our transition metal center, and we end up with these 3, what we call triply degenerate set, meaning they have the same exact energy. So they had the same energy as their component d orbitals before we constructed our molecule. So what happens to the remaining 2? We have x squared minus y squared and z squared. First up, we have dz squared. Now we can see that this has a very different type of interaction between our d orbital centered on the metal and our ligands. We can see that there's a direct overlap between the donut, right, that round piece in the middle that encircles our d orbital in red, and each of our ligand orbitals that are on the xy axes. So all 4 of those can directly interact with the donut of our dz squared orbital. The atoms along our z-axis can directly interact with the lobes that are shaded in blue. So here we can see that the dz squared orbital can have significant interactions with our ligands. So that means that we could construct both a bonding and anti-bonding molecular orbital that uses our set of ligands, or a set of orbitals from our ligands, and the dz squared orbital. Last up, we have our dx squared minus y squared orbital. And here we can see again that there's significant orbital overlap, or we can see that the s orbitals for our ligands can directly interact with each of the lobes for dx squared minus y squared. Because these fall directly along the axis, we can see that there'd be very strong interactions between those 4 s orbitals on our xy axes and the dx squared minus y squared orbital. However, we actually do not have significant interaction along our z-axis here. We can see if we were going to rotate this molecule a little bit, we would see that the orbitals on our z-axis actually lie in nodal planes again for our x squared minus y squared orbital. So we have very strong interactions for both the dz squared orbital and our x squared minus y squared orbital. So let's look at what happens to our molecular orbital diagram when we take into account the dz squared and x squared minus y squared orbitals. So if we're going to look at just the x squared minus y squared orbital and z squared orbitals on our metal, we can see that we can form bonding and anti-bonding molecular orbitals by mixing those with our component ligand orbitals. And so right now, as far as we're concerned, we're going to say that we're just calling these bonding and anti-bonding. This harkens back to the molecular orbitals we were already building, right, where we have constructive overlap, which we are going to be calling these bonding orbitals, and destructive overlap, which means that we are going to be forming these anti-bonding orbitals. And so now we can start to see how we actually generate different types of molecular orbitals when ligands interact with our metal. So if we're going to put this whole picture together, what we're going to see is that we have these 3 different sets of orbitals, right? We have some low-lying orbitals that are our bonding orbitals that occur from the mixing of our ligands with our x squared minus y squared and dz squared orbitals. We have some non-bonding orbitals, and that was our xy, xz, and yz orbitals that originated on the metal. Again, these just don't have any significant overlap with our ligand orbitals, and so we can't form a new molecular orbital that contains both these orbitals and our ligands. Lastly, we have essentially these anti-bonding orbitals that are these high-energy orbitals that result from the destructive interference or overlap of our ligand orbitals and either dx squared minus y squared or dz squared. So how does this work when we're thinking about an actual MO picture? Well, what we can look at is the mixing of these ligand orbitals with our metals. And what we see is that these bonding orbitals will in general be filled in by electrons that come from the ligands. What that means is inside this box here, we have what's called the ligand field for a given geometry of a transition metal complex. In this case, this is the ligand field for the octahedral geometry. And what we labeled initially as d electrons when we were doing our electron counting actually go into these orbitals. We've seen this a time or two on our first quiz, and on our first midterm, we had questions that used fields that looked kind of like this or were variations of an octahedral geometry. And these d electrons, again, that come from the metal when we were doing our electron counting, end up in these particular orbitals. What that means is that the dxy, xz, and yz are essentially non-bonding, meaning they're not forming a bond with our ligands. They are localized on our metal center. And these higher energy states, x squared minus y squared and dz squared, are actually anti-bonding orbitals. And this is going to be important to remember when we start thinking about bond length and strength and the substitution of transition metal complexes, is that this high energy state is actually anti-bonding when it comes to the molecular orbital picture. So really what we care about is what's in the box when we're thinking about transition metals. We're going to come back and expand our understanding of ligand orbitals soon. So if we're looking at this, just what's inside the box, this is what we call the ligand field for our octahedral geometry. This is going to be something we're going to draw time and time again, and we actually have some labels that make our life a little bit easier. So that pairing of dxy, dxz, and dyz are what we call our T2G orbitals. Now this might look a little bit familiar because again you can look on your character table for the octahedral geometry and find T2G as one of our irreducible representations. The T here stands for triply degenerate, meaning that there are 3 different states that have the same exact energy. And we know what the G and U stand for in relation to inversion of our within our point group. Sorry. Our high energy states are what we call our EG states. And when we see an E, E means doubly degenerate. So there are 2 states here, or 2 orbitals, that have the same energy. This makes it easier to describe and talk about these sets of orbitals by calling them the T2G set and the EG set. It makes it so we don't have to individually respond or describe our metal-centered orbitals. The difference in energy between these states is a special value that's very well studied for a range of transition metal complexes. This difference in energy is called delta octahedral, or delta O. And this energy is only describing octahedral complexes. So when you are looking at a ligand field for a different geometry, you would not call it delta O, right? You would talk about the difference in energy, so a delta E. But this is a very well-studied term. It has a special name, delta O, because of its applications in spectroscopy. So we are going to be seeing and investigating delta octahedral quite a bit over the next few weeks. So we can look at these orbital sets, and we can understand how these are now our molecular orbitals on our transition metal complex. But it's important to note that these orbital shapes, or this ligand field, right, this pattern that we are looking at, only applied to octahedral complexes. So each geometry that we can study would have its own ligand field, depending upon how our molecule or how our metal d orbitals would interact with a set of ligands. So what we're going to be looking at in our next class and through our next set of problem sets is deriving the ligand field diagram, right, or the ligand splitting diagram for these different geometries, specifically a linear complex, a square planar complex, and tetrahedral complex. So we're going to be looking at these because they will have their own ligand field splitting diagram, and we can approach this using the same method that we did with the octahedral complex. We look at our d orbitals on our metal, we evaluate whether we can create some kind of productive overlap with our ligand orbitals, and that will lead us to the formation of bonding and antibonding, as well as non-bonding, quote-unquote non-bonding, orbital interactions. All right, thank you.